Transmission lines are the backbone of power grid. The cable itself is the core component carrying the energy. But faults can happen anywhere. For example, birds are one of the primary causes of faults in transmission lines. But these are visible, external failures. There's another kind of failure, the one that you don't see from the outside. That's inside the cable itself. For example, the insulation can have hiding defects, such as a crack, in the worst case causing failure of the cable. In this video, I'll answer how do field conditions change at the boundary between materials with different permittivities, and why does it matter so much in cylindrical geometry of a coaxial cable? These are the questions that I want to answer, but first let's draw what happens at the boundary between two materials with different permittivity. So first of all, what is permittivity? We can denote permittivity with the letter epsilon. And this could be the permittivity for the insulation material XLPE. So I'm going to write X here. And that could be around 4. But what does that mean? Well, it has something to do about the polarization of the material. So how the electric field crosses from, let me draw that in yellow. So how the electric field crosses from one side to another across the boundary. So something happens at the boundary here. So let's say the other medium is, let's draw that in green. That could be the air gap. So permittivity for air is 1. But what happens to the electric field when it crosses this boundary? Does it just go straight through or does it bend? And more importantly, does the electric field strength increase or not? And what happens when it increases? I'll try to answer that. To answer this, we need to look at Gauss's law, which we have here. And I'll walk you through these 4 different steps, one by one. For Gauss's law, what we have is that we have 2 different mediums, medium 1 and medium 2. And the essential here is that they have different permittivity, epsilon 1 and epsilon 2. And we have some boundary conditions, so something happens here. How do we find out what happens? This is where we use Gauss's law. So Gauss's law says that the flux density d across a closed surface is equal to the charge inside of that closed surface. This is what the integral says. So we have some area here that we integrate over, and it's a closed area, and the flux density going through that closed area is equal to the charge. So this is what we have here on the second picture. We have some charge inside, and that charge is equal to the flux density going out and the flux density going out. But something interesting happens when we assume that there's no free charges inside. So what we have is that we have the same integral basically. This is why I'm not usually drawing these equations. But we have 0 charge inside. And this means that when we integrate, then we have dn times first part of the surface minus, so this is the first boundary, this is on this side here, and then we have the other side. And that is equal to 0. And if we rearrange that, then we arrive at this equation. How do we come to this equation? Well, the way that we do that is by taking this integral here and then assuming that the height of this surface goes to 0. So we go towards 0 here. And when we go towards 0, then this tangential component of the electric field. So you should imagine that there is an electric field going through here, and that electric field is spatial in all dimensions, meaning that it can go this way, this way, this way, all the different directions. But when we look at it from this perspective here, and we assume that this pillbox, where we look at the actual electric field going through, then if we make this pillbox go towards 0, as we see here, so when that one goes towards 0, then we don't have any component in this direction. We only have the normal component. And the normal component is just the one going straight through. And this is the condition here we have from Gauss's law, which we again can see here on picture 4, that at the boundary condition between the 2 mediums, the flux density of the normal component is the same. And what does this mean? Well, we can relate it to the electric field, because we know that the flux density d of the electric field is equal to the permittivity times the electric field. So we can rewrite this as the permittivity of the first medium times the electric field strength, first medium is equal to the permittivity of the second medium times the electric field strength of the second medium. And this is how we find out how the field inside of the two materials increase, because depending on the permittivity, the field on the secondary boundary either needs to increase or decrease or stay the same if it's the same material. This is what determines the boundary condition, or one of the things. Because we are not totally done, we are missing the tangential component of the electric field. So how do we relate the tangential component of the electric field to the boundary? The way that we do this is by using Faraday's law. So Faraday's law in electrostatics with a conservative field says that the closed loop integral of the electric field around any path is equal to 0. And what this means is that since it's the electrostatic case, there's no changing magnetic flux, meaning there's no extra energy gained by going around this closed path. So let me try to illustrate it by drawing a loop. So we have two parts of the loop. We have the one at the first boundary. So this is at the first boundary, and then we have at the second boundary. Let me draw that in red. And the distances here along the line is the same. So L1 and L2 is the same, but we have different mediums. And the interesting thing is here to see that it's actually different from the normal component case. So if we integrate along these lines, then we have that we have the electric field on the first part of the boundary here times the line integral. And then we are minusing here. So let me just draw the electric field first. We have eT1 going this way. And we have for the other part eT2 going that way. And before we do anything, we also have the height here, h. So when we integrate here, what we have is that we have E1 times L1 minus E2 times L2. What we do then is that we decrease the height. So we make the height go towards 0, just as the other case. And when we decrease this height here, we only have the tangential component, because since there's no height, we don't have any component here. We only have L1 along this side and L2 along this side. So we can rewrite it again here to E1 T is equal to E2 T, where T means the tangential component. So what we have, to sum it up, is that across the boundary for the tangential component of the electric field, we can see that the electric field in the tangential component is the same. So this is different from the normal component, where the normal component was related to the permittivity. The tangential field is the same across the boundary. So these two laws that we just derived count for any geometry. But let's apply them now for the one that we care about, the cylindrical one for a cable. So we have two radiuses in a cable. We have the inner one of the conductor, denoted by small r, and then we have the outer one to the end of the insulation, in this case denoted by big R, and then we could have another one too called X, which we can vary between these two radiuses. And what we have is that on the surface of the conductor, the electric field is at its highest because of the relation between the electric field and the gradient of the voltage. So there's another video about this. And these equations over here is what governs the electric field of the cylinder. So this is again from Gauss's law, as we had before, but just in cylindrical geometry. And when we integrate this, then we get this equation here, and we can rearrange for the electric field, which depend here on the charge. But if we remove the charge from the equation, then we have an expression that is dependent on the voltage. So the interesting part here is that it's dependent on how far away we are from the inner conductor. So it decreases by 1 over x. This is one thing to notice. So E decreases by 1 over x, meaning that the further away we get from the inner conductor, the less field strength we will have. And another thing to notice is that where is the ideal conditions? So how can we minimize the electric field inside of this coaxial cable? We are interested in that, and the reason we are interested in that, I will show you the final part. But how we do this is by optimization. So we take the electric field and then we differentiate it, as we always do, with respect to the radius, the inner radius. And we want to find when this is minimal. Then we'll find a minimum, and that minimum we're interested in to keep the field as low as possible throughout the coaxial cable. And that is a ratio that is given, and that is the outer radius divided by Euler's number. And we can also write it as R times 0.37. So ideally, when you design cable, you're going for this radius. This is the baseline that the cable needs to withstand, even without any void. But what happens when we introduce a cavity in the cable? We have the same geometry as before. We have a small radius, R, and we have a big radius, big R, to the outer sheet that is grounded. And inside we have some electric field that is inhomogeneous, as you can see here. Let me try to draw an arbitrary electric field line here. Could look something like this, going into the material. So here we have one field strength in the insulation material, and then we have another inside of the cavity, E2, and then we have another one going out. So I'm just drawing the lines here at random, but we know from before that we have a normal component N, and we have a tangential component T. And we know that the normal component is dependent on the difference in permittivity. So we can write this. Let me first write the actual permittivities. Permittivity of cavity, let's assume that it's air, then it's 1, and A for air. And let's write it with green for the insulation. So permittivity of the insulation, and assuming that it's a XLPE cable, then that would be 4. So what does this mean, and how does it relate to the electric field inside and outside of the cable? Well, here we can have the equation that we derived from Gauss's law and relate it to the actual electric field here. So this is the effect that it has, and we see that it has an effect on the actual electric field inside of the cable. So it's increased by a factor of the permittivity. And how can we actually determine this? Let me try to write the equation that we had from before. We have that the electric field across the boundary, the normal component of the electric field across the boundary, is the same. And this is what I'm writing here. And we know that some of these values are fixed. So this is a material constant. And if this is the first boundary, that is the XLPE insulation, then we know that this is 4. And let's assume that the electric field here is 1. And then we know inside of the air gap, the permittivity is 1. So what happened to the electric field inside of the air gap? Well, we can rearrange this equation, and by knowing the actual electric field and relating it to this equation here, then we get this equation, meaning that inside of the air gap, we would actually have an increase of 4 times the outside electric field strength. This is why the electric field and the enhancement of the electric field because of cavities can be so dangerous in coaxial cables and high voltage cables, because it causes stress in the material and in worst case can cause breakdown between the two layers. So back to the cable cross section. The crack you can see from the outside follows the exact same rules as the field around the conductor itself. That's the whole story.